Hello and welcome back to part 4 of chapter 14, Chemical Kinetics. In this part we're going to look at some of the changing conditions and what their effect can be on the rate of a reaction. And specifically for temperature, we're going to look at the Arrhenius equation, which is a way for us to correct for those changes when we change the temperature and see what the effect is on K and other components. So we've talked about earlier that changing the temperature changes the rate constant of the rate law. That's the only thing that's going to change the rate constant itself. Now you can change concentration and you can do different things and change rates, but the rate constant will be the same. And so this relationship is defined by the Arrhenius equation, and there are many forms of the Arrhenius equation. This is one of them. But they all use the same factors, but you can kind of rearrange them a little bit. T has always got to be in Kelvin, so don't forget that, just like in the gas laws when we had those. This time the gas constant we're using is the one for energy, so that's 8.314 joules per Kelvin mole. The E sub A is the activation energy. That's the energy required to start the reaction. And then A is a constant that's referred to as the frequency factor, and the rate that the reactant energy approaches the activation energy. And so if you think about this would be a pretty short A because it's going to approach that quickly. If it does more like that, that's going to be a larger A because the rate that it's approaching the activation energy is going to be a lot lower. So A is something that is defined, predetermined. So there's an energy barrier to almost every reaction there is, and that's the activation energy is how much it takes you to get to that activated complex. That once you get to the activated complex, and the other word for that is transition state, you get there, and once you get to that, then your reaction will go. So it's how much energy it takes to get you to that transition state. And that complex, that activated complex up there, is where you've broken some bonds in the reactants and created other bonds in the products. And so that's where you are at this, the top of the curve, so to speak. So you have an energy level that you're starting out with your reactants, and so you have a few things. You have 2 moles of hydrogen gas in the white and a mole of oxygen gas, and the amount of energy it takes for this reaction to occur is the activation energy, okay, which is going to be this much energy, okay. Once you get to that point, you've put that much energy in, you're going to be at the activated complex. And so that's where these guys have moved up here and are starting to break bonds, okay, and make bonds. And then once you have gotten to that point, then you're downhill, okay, so the energy is downhill, and you're going to form your compound, 2 moles of water, and then your energy of the products is less than the energy of the reactants that you started at. And you may remember this from Chem 1. Okay, so we've seen this actually before. The Arrhenius equation, I showed you the crazy looking one with, e to the whatever. The Arrhenius equation that we use is called the 2-point form, and that's because we are comparing 2 different temperatures. And so the natural log of the K of the second reaction divided by the K of the first reaction is equal to the energy of activation divided by 8.314 joules over K mole times the reciprocal of T1 minus T2. And so this is the 2-point because we're looking at two data points at 2 different temperatures. And so I know that this, sometimes people look at this and, oh my gosh, it's got natural logs and reciprocals and all that. And so I've found that it's easier to think of it in terms of A, B, and C. You have an A term, which is your natural log part. The B is the activation energy over R, and then C is going to be your temperature. And it's it's very simply A equals B times C. And so you kind of keep those together in your head when you're working these problems, and then it's not quite so difficult to interpret. And so in the example I have for you on the 2-point form of the Arrhenius equation, you've got nitrogen dioxide that's reacting with carbon monoxide, and my arrow should be up there, going to nitrous oxide or nitrogen monoxide and carbon dioxide. And the rate constant at 701 Kelvin is 2.57 meter minus 1 S minus 1. And at 895 is 567 meter minus 1 second minus 1. And it wants us to find the E sub A for this reaction. All right, so we're looking for E sub A. All right, so first I'm going to take inventory because I've got several different things that I need to make sure that I remember. Now I know it's got two different temperatures and I'm finding activation energy, so I know that I'm using this particular equation. And so I'm going to leave it in that form until I get to the end, because if you're looking for one of these K's, then you don't want to do this natural log until the end. So that's my A, right? And then E sub A over R, and then times 1 over T1 minus 1 over T2. All right, so that's our form. All right, and so I need to know, all right, so I know I've got R is 8.317 joules over mole K. And I've got T1 is 701 K. And I've got K1 is 2.57 molar minus 1 second minus 1. Then I've got T2, which is 895 K. And I've got K2, which is 567 meter minus 1 second minus 1. And so I'm finding E sub A. All right, so I have every number except E sub A. So really all I'm doing is I am just plugging numbers into this formula. So I'm going to go ahead and do that. So the natural log of 567 meter minus 1 second minus 1 divided by 2.57 meter minus 1 second minus 1 equals my unknown, which is E sub A, divided by 8.314 joules over mole K, times 1 over 701 K minus 1 over 895 K. And just make sure that you're getting the right ones in there. That's why I always go ahead and take inventory before I do it. So I've labeled everything so I know that I'm going to then be writing the correct thing in there. And so when I take the natural log of 567 divided by 2.57, I'm going to get 5.40. And that won't have any units because meter minus 1 second minus 1 are going to cancel. And so I still have my E sub A divided by 8.314. And then I am going to do 1 over 701 minus 1 over 895. Which that comes out to 3.09 times 10 to the minus 4 over K, right, because the K's were on the bottom. Then I just have to rearrange, okay. Let's say, all right, so let's say, so I'm going to do one, I'll write this intermediate step for you, E sub A times 3.09 times 10 to the minus 4 over K times 8.314 joules over K mole, right? And then 5.40, let's see, 5.40 times, now I'm going to bring them over, okay, so I'm going to bring those over, so that's going to be, no, wait a minute, take that off for a minute, sorry. It's going to be 5.40, oh, I know what I'm doing. I already did the E sub A. The E sub A is equal to 5.40 divided by 3.09 times 10 to the minus 4 over K times 8.314 joules over K mole. I'm just rearranging it, so if you can tell what craziness I'm doing. All right, and so that's going to end up giving me 1.45 times 10 to the 5th joules per mole. And I believe it wants it in kilojoules per mole, so then I'm going to have to multiply that by 1,000, or divide by 1,000. 1 kilojoule, running out of room. 1 kilojoule per 1,000 joules, and that's going to give me 145 kilojoules per mole. Okay, so let me make sure I didn't lose you on this step back here. All right, so here I was with this step. All right, and then I was going to change to make E sub A equal to, so just forget that. So E sub A is equal to 5.40 times K over 3 at 0.09, or divided by 3.09 times 10 to the minus 4 divided by K, times 8.314 joules per mole K, and then that gave me the answer in joules, and then I made sure that I read what I was asking for, which was kilojoules, so I just had to transfer that at the bottom. Where this gets a little fun is if you're solving for one of the temperatures, okay, or if you're solving for one of the Ks. So you just have to really watch what you're doing and see what it's asking you for, and make sure that you're paying attention. And so here's your practice where you're going to use the same results that you had in the previous example, but you're going to compare either one of those temperatures and find the rate constant for the reaction at 525. So this time you're going to be solving for K2, all right? And so you just have to, when you're doing that, just leave that natural log until the very end. And you know how to get rid of a natural log, right? If you've got a natural log, you raise both sides to the minus ln, okay? So you raise both sides to that ln, right? E to the whatever, all right? And that makes it regular ln. And so you have to raise the other side to the e power, and that's how you get rid of it. So again, if you don't really remember how to do this stuff, then look back and see. But this is one that you're supposed to practice on, so that's why I'm not working it for you. And I have every confidence in you that you can do it. Some of y'all are like probably thinking, oh my gosh, my math skills. Don't worry, practice. Go back, look at those tutorials in mastering. The math tutorials. There's also chemistry tutorials for some of the stuff you should have learned or should remember maybe from Chem 1. So you can go back and do that at any time.